Hello everyone. My name is Vanshaj Khattar, and today I am excited to present some of our recent research that we have been doing, which is on critical load restoration under changing topologies. This work has been done in collaboration with National Renewable Energy Lab. Let's go to the next. To briefly introduce myself, I am currently a fourth year PhD student under the supervision of Dr. Min Jin, and my research interests lie in reinforcement learning, optimization, and control. The problem we have been seeing increasing US like power outages inside the US and also worldwide because of many extreme events such as storms, um, tornadoes, or even cyber attacks. And these graphs on left and right show the statistics on how these worldwide events have been increasing over time. So there has been an increasing emphasis on making the grid more resilient to physical and cyber disturbances. And one of the potential solution is to use a microgrid. And a microgrid is a group of interconnected loads and DERs that acts as a single controllable entity with respect to the grid. Uh, so that's why the problem of critical load restoration comes in inside the microgrid. So in case there is a power outage, you could actually restore some of the loads by controlling this distributed energy resources. And the goal in this critical load restoration problem is to reliably restore as many critical loads as possible in the restoration stage using local DERs. And these DERs are like renewable based or fuel based generators or energy storage generators. And the main goal is to do the optimal scheduling of these DERs generation and load pickup under the uncertainty of operational renewable generation system topology. And we make two main assumptions in this work. First is dispatchable DERs have limited energy capacity and they should be leveraged to maximize load restoration. The second assumption is we focus mainly on scheduling DERs and load pickup, and their dynamic performance is not considered for simplicity. It shows the main problem formulation of the critical load restoration problem, and this could be framed as this optimization problem, where this RTCLR plus VT denotes the objective function. RTCLR denotes the how much reward we are restoration reward, which is combined of the amount of power that we're able to restore when the load shedding penalty, and the VT is the voltage violation penalty. That is basically voltage violation that is happening on each of the bus, and it is subject to all of these constraints. Here are four constraints are shown, which are include DER operational constraints, load constraints, power flow constraints, and reconfiguration constraints. And in our case, our main goal is to divide the problem into two things: CLR agent and the COR agent. And it will be discussed what how their states are: PV forecast, load condition, battery, and the actions are the P slash Q of PV batteries and peak load pickup decision. And action in the COR agent is trying to control each of the CLR agents. And this will be discussed in the next upcoming slides. Main challenge in distributed load restoration is the DER uncertainty, topology changes, and multi-step decisions. And the existing solutions are kind of could be categorized into two main methods: OPF or model-based methods, which use optimization-based strategies, and the second one are the reinforcement learning-based solutions, which use learning-based strategy to do the critical load restoration. And these are the recent works that have been shown that have been done in each of these categories. Well, why should we use reinforcement learning over optimal power flow solutions? Reinforcement learning actually allows us to adapt the agent's decisions as the environment is evolving, and the reinforcement learning is able to handle the ER uncertainty, and the online implementation of policy streams avoids solving complicated, robust, or stochastic optimal power flow solutions, which could be computationally expensive to deploy in real time. And sometimes there could also be topology uncertainty. Maybe we could have lost some lines or nodes after an extreme event occurred, and the DERs along with them for a certain period. And also, this information like topology change could not be observed. Proposed method to overcome the topology uncertainty is to model the underlying critical load restoration environment as a graph, which enables the RL agent to handle the topological variations during the load restoration. There are three main ideas. The first one is to we divide the underlying environment into different cells so that they could be independently controlled. Second is that we model the underlying environment as a graph, so we use a graph neural network. And third is that as the topology changes, what happens is that the actions available to each of the agent also changes. So we use a concept of action masking, like some of the actions that have to be informed to the agent that they have been masked. And this depends on the underlying topology. So we use a topology dependent action masking. And combining all these three, we get our method, which we could use for the critical load restoration under changing topologies. This slide shows the overall high-level idea behind our method. If we see at the lowermost, there are like different cells, microgrids that we have divided. So this is a sample for 4 microgrids. If we divide them into 4 microgrids, each of these microgrids can be controlled by each of the CLR agent. As you can see, 4 CLR agents. And as this is a hierarchical approach, there is also a coordination agent which is controlling each of the CLR agent and is able to coordinate the power flow that it could happen in between the CLR agents as well. So, and what you see in between is a topology identification module that will be discussed in the next slides, and a topology dependent action masking. So each of these CLR agents are working independently to control each of their microgrids, and the coordination agent is letting the power transfer to happen between each of the CLR agents. And that is why we call this a hierarchical graph multi-agent RL, as we are also using a graph neural network which takes in the state and puts in the graphical encoding to each of the CLR reinforcement learning agent. We'll describe in detail how do we do the real-time topology identification. Firstly, it should be noted that the topology information of each cell is never directly observable. The only observable states are the voltage and power measurements at each bus location. So what we do is that we train a multi-layer perceptron on the extracted features from the voltage and power measurements. And what we see here are this is the overall high level diagram of a capsule graph neural network that we use, and the microgrid on each cell, the graphical and the non-graphical features are exploited. So to train the topology identification module, we use the multi-layer perceptron and the three features, which are the voltage correlation feature, voltage drop fluctuation feature, and the power flow feature, which was also done in one of the recent works. And using the adjacency matrix and this topology identification can give an idea to the graph neural network of what is the underlying topology. And combining all of this, we get the overall state encoding that can be used by the critical load restoration agent. In, discuss one of the case studies. So what we do is we do a case study on a modified IEEE 123 bus system. And the base reinforcement learning agent that we use is a multi-agent deep deterministic policy gradient method as our base multi-agent reinforcement learning algorithm. And here on the left side we are showing the overall modified 123 bus system. And here what we see is that in the black buses shows the cell 1, which we have divided into like the agent 1 that will control this side, and then there is cell 2 shown in red, which is will be controlled by the agent 2. And in pink what you see is the cell 3 that we have divided, and all these pink buses denote the cell 3, and between these are the tie switches shown as red and green. And for topology changes, we consider that these green or red ties and sectionalizer switch could go from open to close or vice versa. So um, for testing and training, we are showing the topology changes in yellow and red crosses. So for training, we are having the buses 3 and 4 getting removed, the sectionalizer switch, and that is what we do the training on. And for testing, we do the testing on when the sectionalizer switch between 54 and 55 closes, or basically opens up. So these are shown as like different scenarios that are possible. So as we can see, we consider and compare our HG model method to the basic identical and basic MLP method, where basic identical we do not use a graphical neural network, and in basic MLP we use multi-layer perceptron as a graph instead of a graphical encoding. And what we see is that the HG model method is able to restore the maximum load in each of these cells denoted in black, red, and pink. Uh, and similarly, we see similar kind of trends in the next table for another scenario for testing, where HG model is able to restore maximum load um, in each of the cell after there is an outage. Finally, I also discussed the critical load restoration performance, and there are, you can consider it as three columns: the left column, the middle column, and the rightmost column. So if you look at the left column, this is the HG model, and the middle column is the basic MLP, and on the rightmost column is the basic identical. So if we just look at the leftmost column, what we see is that in black is the total requested load for a 3-day period, and the pink, or the basically the red one, is the total requested critical load. And what we see is that in HMRL, the green, basically the total supplied load, always stays above the total requested critical load in all of the three cases. But what we see is that in the other two cases, if you look at the second and third column, this total supplied load actually does drop between the total requested critical load at certain time steps, which shows the advantage of our method over the other methods which do not use the graphical representation or the topology dependent action masking. And these results show the overall advantage of our method. To conclude the overall method, we proposed a graph-based hierarchical RL-based approach to handle this critical load restoration problem under changing topologies, which has not been addressed in the literature yet. And there were three main components. We firstly divide the underlying microgrid in different cells. Then we model the problem as a graph using a graph neural network. Then finally we use a topology dependent action masking, which informs the agent about the underlying topology. For the future work, this work could be extended to like ADMM optimization based plus RL based hybrid approaches, and this could be tested on more extensive topology changes. Thank you for listening, and if you have any questions, please let me know.